The work, energy, and power section of the 2020 physics paper starts with a multiple choice question 1.5, which reads, the base SI unit of the physical quantity work is, and so we start with our formula for work, where work is the product of force and displacement. And that means that the units for work, we show units by writing something in square brackets. The units for work are equal to the units for force, which is newtons, multiplied by the units for displacement, which is meters. But what we can see here is that they do not want units, or they do not want newtons. So what we need to do is we need to find out what the units are for force, what a newton actually is. And we do that by saying that 1 newton is actually equal to the unit for mass, which is the kilogram, multiplied by the unit for acceleration, which is the meter per square second. And so what we can see then is that the units for work is equal to the product of kilograms, meters per square second, multiplied by meters once again, and therefore kilogram meters squared per second squared. And so our correct answer is option C. Question 5 reads, a roller coaster car of mass 200 kilograms, where the engine switched off, travels along a track ABC, which has a rough surface as shown in the diagram below. At point A, which is 10 meters above the ground, the speed of the car is 4 meters per second. At point B, which is at a height h above the ground, the speed of the car is 2 meters per second. During the motion from point A to point B, 3.4 times 10 to the 3 joules of energy is used to overcome friction. Ignore the rotational effects due to the wheels of the car. And so we start here by noticing that they tell us that this track has a rough surface, and then they emphasize that again by telling us that there's a certain amount of energy used to overcome friction, which basically means that there's energy being lost, which means that the energy in the system is not conserved. Question 5.1, define the term non-conservative force, and the definition as it is given in the guideline document is that a force is non-conservative if the work it does on an object between 2 points depends on the path taken. And as we can see, the emphasis here is on the work that it does, and it is dependent on the path that is taken. Question 5.2 asks, calculate the change in kinetic energy of the car after it has traveled from A to B. And we do that by starting with a formula that says that the change in kinetic energy, delta EK or delta K, is equal to the final kinetic energy minus the initial kinetic energy. And we can then do that where we say that is the 1/2 mass times the final velocity squared minus 1/2 mass times the initial velocity squared. The mass of this roller coaster car remains the same at 200 kilograms. The final velocity at point B, we are told, is 2 meters per second squared minus the mass, which again is unchanged at 200, and the initial velocity, which was given as 4 meters per second squared. What that tells us is that the change in kinetic energy of this roller coaster car between points A and B is negative 1,200 joules, which tells us that 1,200 joules of energy is lost, of kinetic energy specifically is lost. Question 5.3 asks us to use energy principles to calculate the height h. There are, once again, a number of ways in which this can be done. This can be done using the work done by the non-conservative forces equal to the change in E mech, change in the mechanical energy. We could also use the work energy theorem that says that the net work done on this object is equal to this object's change in kinetic energy. Again, either solution would be correct, either solution would get the marks. I'm going to use the first formula here, work done by the non-conservative force. In this case, we know that there's only one non-conservative force acting on this object between point A and point B, and that is the friction force. And we have been told exactly how much energy or how much work is done by that friction force. The one thing to remember here is that we are told that this energy is used to overcome the friction. What that means is that that energy is lost, and so we need to show that the energy is lost by saying that is negative 3.4 times 10 to the power of 3 joules of energy that is lost, and that is equal to the change in mechanical energy, which we know is the change in kinetic energy plus the change in potential energy, where the change in kinetic energy we've calculated in the previous question, and so we can simply substitute that 1,200 joules of kinetic energy that we know has been lost in, and then we have our change in potential energy, which is the mass of the object multiplied by the gravitational acceleration, multiplied by the final height of this object, minus the initial height. We are trying to find the change in height here. And then we substitute once again the values that we have. We have the mass of the object. Gravitational acceleration is a constant. The final height is our unknown, and the initial height we have been told is 10 meters. And so we solve for our one unknown here to find that the final height of this object is 8.88 meters. Question 5.4. On reaching point B, the car's engine is switched on in order to move up the incline to point C, which is 22 meters above the ground. While moving from point B to point C, the car travels for 15 seconds at a constant speed of 2 meters per second, while an average frictional force of 50 newtons acts on it. Calculate the power delivered by the engine to move the car from point B to point C. And once again, as with many of the work energy power problems, there are a number of possible ways to solve this. The first way is once again using the work done by the non-conservative force, which is equal to the change in the object's mechanical energy. We could also have used our work energy theorem, which says that the net work done on an object is equal to the object's change in kinetic energy, or we could have used Newton's second law, which says that the net force is equal to the mass times the acceleration of this object. I've chosen to use the formula for work done by the non-conservative force because then I do not need to take into account the weight force, which can make it slightly more complicated, but once again, the choice is yours. The answer remains the same. So what changes now is that there are now two non-conservative forces acting on this object. There's now the work done by the engine, and there's still a frictional force acting on this object, and those are both leading to a change in the mechanical energy. The change in the mechanical energy here is now a change in the kinetic energy, 1/2 mvf squared minus vi squared, and the change in potential energy, m times g times the final height minus the initial height. What we can do now is we can see that since this object, or since this car was traveling at a constant speed at a constant speed of 2 meters per second for 15 seconds, we can therefore say that the distance covered in that time is equal to 15 times 2. It covered 30 meters of distance. This is important because now we know what distance the engine and the frictional force are doing work for, and we can say therefore that the work done by the engine plus the work done by friction, which is the force of friction, multiplied by the displacement of 30 meters that we have just calculated, multiplied by cosine of 180, because friction and motion are always opposite to each other, which shows that friction is removing energy from the system, and that is then equal to 1. The change in kinetic energy, which is 0 because we were told this object is traveling at a constant speed up the slope, and then because we have the mass of this object, the gravitational acceleration, and the final height given as 22 minus the initial height that we calculated, the height at point B of 8.88, then we can solve for our one unknown, which here is the work done by the engine, which we found to be 27,215.2 joules, which is positive, which tells us that the engine is adding energy to the system. And finally, we then answer the question, which is asked for the power of the engine, where we say power is the amount of work done divided by the amount of time, the amount of work done, 27,215.2, divided by the time. This motion took 15 seconds, and therefore the power we can say is 1,814.35 watts. Once again, this could have been done using our work energy theorem, where we say the net work done on the object, where the net work is the work done by the normal force plus the work done by the engine plus the work done by the force of gravity plus the work done by friction, where the work done by the normal force is obviously 0. The work done by the engine is our unknown that we want to calculate. The work done by the force of gravity we can calculate because we know what the change in height of this object is, and the work done by friction we can calculate as we have done with the previous example. Again, either one of these would get you exactly the same answer. The one that's slightly different is if you use Newton's second law to find the net force acting on this object, and then using that net force along with the formula P average is equal to force times velocity, we could also have reached the same answer. When marking questions like this, once again, the definition, when we are asked for a definition straight out of the guideline document, it is important, and there are words that are important, and the word order is important. And a non-conservative force is one for which the work done is independent of the path that is taken. Then for question 5.2, where we are asked a fairly simple substitution calculation, it is always going to be 1 mark allocated for a formula as it is given in the formula sheet, 1 mark for the correct substitution, and 1 mark for the correct answer with the correct units. Important in the work energy power section, a negative sign is important because it tells us that energy is being removed. Question 5.3, again, there would be a mark for the correct, or using a formula, no matter what formula it is. Then there is a mark for correctly realizing that the work done by friction is negative and must be subtracted. Work done for correct substitution, or sorry, 1 mark for correct substitution and 1 mark for the correct answer, once again with a correct unit. A question like 5.4 normally has positive marking, basically saying that if you had made a mistake in this value over here, but correctly substituted that in for your further calculations, you could still get all the marks for question 5.4, despite the answer being wrong. But once again, there is a mark allocated for a correct formula. There's a mark allocated for showing the understanding that the friction force acts for 30 meters, where you've done some kind of calculation that shows how you found or how you arrived at that answer. And then again, a mark for finding the amount of work done, and then a mark for your final answer. So all of these questions, it is always important to show that you understand what formula you are using, that you start out by identifying the formula that you are using, and then that you can correctly follow that through and find your final answer, once again, with the correct units.